So this is the example I'm mentioning, the new one I added. So one of the main reasons I want to include this example is actually to show how we do in linear interpolation. So the table, that table 10.10 only contains value at basically 0.1, 0.2, 0.3, so that 0.1 interval for M and N. So if you have values in between these, how do you do interpolation? How do you get I3 values? So this actual example, it's a uniformly loaded rectangular area. So a given surface pressure, 2,000 pound per square feet. So Q is 2,000. And we are asked to determine the vertical stress increase below point A. So point A, the location of this point A is given. It's within this rectangular loaded area at a depth Z of 60 feet. So to use that solution of stress increase below the corner, we first need to divide this large rectangular area into smaller ones such that this point A is at the corner of each small rectangles. So we can divide this large rectangle into 4 smaller rectangles. I'm going to label them 1, 2, 3, and 4. And then point A is at the corner of each of these 4 small rectangles. So we can use that solution, that table 10.10, to find that I3 factor for each of them. And then we add them to get the total stress increase. So that's the approach we're going to take. So basically delta sigma Z. And this I3 for this example is the sum of basically 4 small rectangles. So it comes from, we call I3 1, rectangle 1. I3 4. So we can find the influence factor for all these 4 small rectangles, add them up, then multiply that by Q to get stress increase. So that's the approach we're going to take. And as I mentioned at the beginning, the reason I picked this example is you need to do interpolation. And just very quickly, for linear interpolation, so suppose we are given 2 points, let's call it that x1, y1, and x2, y2. And we want to get the y value at a new location. So say for xy. So these are given. So you can use simple linear interpolation to get y value at a new x. So this is and this is basically the equation we're going to use for linear interpolation when we use that table 10.10 to find I3 values at some intermediate MN values. And we're going to actually apply this multiple times. So this is one way, one approach we're going to take. And the second approach, as I mentioned, we're going to use that figure as well. So you can also use the figure to get I3 value for given M and N. So let's use table first. So I'm going to start with rectangle 1. So let's call this 1, 2, 3, 4. So for the first rectangle, in B and L values, you can read these from this figure. So B is 10 feet. We call the smaller dimension B, and the larger dimension L. And Z, of course, 60. And from this, we can calculate the M and N value. So for this one, M is 10 over 60. 0.167, and N is 20 over 60, 0.33. 0.333. So let's keep 3 digits here. So that's the M and N value. So now let's look at that table 10.10, that solution. So notice that 3.33 and 0.167 are not on this table. And the way to get I3 value is through linear interpolation. And because we have both M and N in between values on this table, we have to do linear interpolation multiple times. So I'm going to linear interpolate in the N direction first. So from table 10.10, so we keep M at 0.1. And then n value 0.33 is between 0.3 and 0.4. And 0.3, 0.4 are both in that table. So for n of 0.3 first, and then we'll look at n of 0.4. The I3 value for m of 0.1, n of 0.3. Let's look at this table. M of 0.1 and n of 0.3 right here. That's 0.0132. And for n of 0.4, I value, or I3 value is 0.0168. And these two values we can read directly from the table. So that's 0.0132, 0.0168. So we got these two values directly from that table, 10.10. And then using linear interpolation, we can get the I3 value for n of 0.033 or 333. And I'm going to use that XY equation I just showed it on the previous slide. So this is I3 will be your Y value, and here n will be your X value. So that's basically that equation for linear interpolation, and the value for I3, 0.01439. So that's the first I3 value for m of 0.1 and n of 0.33. And then we can repeat this for m of 0.2. So for m of 0.2, we repeat this process. We can read I3 values for n of 0.3 and 0.4 from that table again. Let me go to table 10.10. So this time we're looking for m of 0.2 and then n of 0.3 and 0.4. So that's 0.0259 and 0.0328. 0.0259 and 0.0328. So you can get these two values directly from the table, then linear interpolation again for n of 0.033. And I'm not going to write that equation again. So basically, same linear interpolation equation, just replace that n and I values. So I3 this time is 0.2818, or 0.02818. So that's I3 value, 0.02818. So once you get these two values, then finally for that m value of 0.167, so that's the m value for this rectangular one, we need to do another linear interpolation. So this time, n value is 0.333. And from these previous two steps, we know for m equals 0.1, I3 is 0.01439, and m of 0.2, I3 is 0.02818. And this time linear interpolation again, but this time the x will be your m, and y still is I3 this time. So I3 value. So again, I'm using that same XY equation for linear interpolation, but here y is still your I3, but x is m because we're interpolating along m direction. And this is 0.0236. And this is, let's call this I3, I31. So this is I3 value for that small rectangle one. So basically we did that the interpolation calculation 3 times to get this value. So that's one way to get this I3 value for these intermediate m and n values. And the second approach, as I mentioned at the beginning, is to use that figure. So I'm going to show using this rectangle one, again, how do you use that figure to read I3 values? That figure is this one here. So this is figure 10.24, and this is a log scale on the y-axis. So notice this M is in log scale, and all these values on this curve are N values. So to read the I3, which is your y-axis, we're going to first find N value on the x-axis. So M, remember for rectangle one, M is 0.167 and N is 0.333. So that's the M and N value for that small rectangle. And to read values on a log scale, let me use from 10 to 1. Okay. If you look at log scale, you see all these minor ticks. So that's 1.0. And if you move to the left, so this is plotted from large to small, from left to right. So if I move to the left, so this is 2, 3, 4, 5, 6, 7, and 10. So that's increased by 1. And then from 0.1 to 1.0, each minor tick represents 0.1 increment. So that's the first note on reading on a log scale. And the second note, this is a pretty useful equation to know. So on a log scale, so let's say from point, let's call this point A and point B in log scale. So many students have asked me, how do you read on log scale if your value is in between these ticks values? So if in between, say, 1 and 2, or in between 0.1 and 0.2. On a log scale, for these two values, let's say it's 0.1, 0.2, or 1 and 2, the geometric mean on the log scale. So geometric mean, so basically the center of these 2 points on the log scale, the equation for that is actually square root of AB. So that's one way to help you identify, pinpoint the value on log scale. And you can do this, you can repeat this for this midpoint as well. Let's say A is, let's use 0.2 here, and B is 0.1. So the geometric mean, that middle point is square root of A times B, which is square root of 0.1 times 0.2, and that value is 0.141. And again, you can repeat this for this geometric mean point, and this will help you pinpoint and revalue on the log scale. So using this, let me see if I can zoom in a little bit here. Okay. If you look at this plot here, I actually added 2 vertical lines here. So this is 0.2. The geometric mean between 0.1 and 0.2. So this value here, using that formula I just mentioned, this is 0.141. And then if you take square root of 0.2 times 0.141 again, you can identify this point as well. And this point is 0.168. That's a geometric mean between 0.2 and 0.141. And then remember the M value for our problem for rectangle 1 is 0.167. So it's very close to this 0.168. So that's fairly close. Let me zoom out a little bit. So then we can draw a vertical line corresponding to this M of 0.167. So this line corresponds to, so that's the M value. And then this M value, this vertical line, is going to intersect your N curves. So N curves, our N value is 0.333. So it's in between 0.3 and 0.4. So let's look for the intersection with 0.3 and 0.4 curve. So this first intersection, this is with that 0.3 curve. So this is N of 0.3. And then look for the other intersection with 0.4. So that gives you the second intersection. And then you can read these two values from this curve. So again, let me zoom in a little bit. So the first one, the lower value, this intersection. So this is about 0.022. This is a y value. And then the other value is this one. That's the I3 corresponds to n of 0.4 and m of 0.167. That's about 0.028. So let me zoom out. So basically read these two values from this curve. So we have, so for m of 0.167 and n value of 0.3, we get I3 value of 0.022. And for n value of 0.4, we get I3 value of 0.028. And then for n of 0.33, you can again use a simple linear interpolation to get this. So I3 value for this case is about 0.024. So that's if you use this figure to get I3 value. This involves a minimum interpolation, just one last step. And for the other two values, you read directly from this figure. And if you compare this with the value we got from interpolating values from table 10.10, it should be fairly close. So this is 0.024. And the value we interpolated from table 10.10 is 0.0236. So it's pretty close. So basically, if you have values of m and n not in that table, you can either using interpolations, which may involve multiple interpolations, or you can directly use that figure 10.24 to read I3 values. So that's rectangle 1. So I spent more time on this one. And for the other 3 rectangles, it's basically a similar process. So for rectangles 2, 3, and 4. So rectangle 2. So you can just follow the same process using either that table or figure 10.24. So this rectangle 2 n value is 0.333 and n value is also 0.33. So I3 for rectangle 2, this is 0.044. And for rectangle 3, n value is 0.5. And n value is 0.167 in the I3 value. And for the third rectangle, it only involves one linear interpolation because n value 0.5 is in that table. So this I3 for the third rectangle is 0.0324. And then the fourth rectangle n value, this is 0.333 and is 0.5. And I3 value is 0.0639. So once you have all the I3 values, then you can add them up, calculate the final stress increase. So the final I3 value for that large rectangle. So you can add them up, and then the stress increase Q times I3. And this is 2000 times, you just add all these I3 values. And this is 328 PSF. One thing I want to mention here, for table 10.10, actually m and n values are interchangeable. So you notice here for this third rectangle, I actually used the larger dimension to calculate m. So you have a larger value in m. So m is 0.5 and n is 0.167. And if you use m of 1.167, so if you say set m of 0.167 and n of 0.5, so basically you use the smaller value for B to calculate M and the larger dimension for L to calculate N. And if you look at the table, you get the same I3 value. So M and N values for that table 10.10, they are interchangeable. It's this one here. So let's pick any values. Let's say M of 0.5 and let's use N of 0.1. So that's 0.0198. And then if you look at M of 0.1 and N of 0.5, it's also 0.0198. So for this table, it really doesn't matter if you use the larger one for B or a smaller one for B. So either way is okay. Any questions for this example? Again, as I mentioned at the beginning, the main reason I picked this example is because it involves reading I3 values not in that table. So it involves multiple linear interpolations. It also involves using that figure 10.24 to read I3 directly from the graph.